Among all the possible patterns that are found in numerical data, the normal distribution is overwhelmingly the most common. This symmetric, unimodal, bell-shaped curve is pervasive throughout statistics. The normal distribution always describes a symmetric, unimodal, bell-shaped curve. However, these curves can look different depending on the details in the model. Specifically, the normal distribution can be adjusted using two parameters, the mean and the standard deviation. So what the mean does, the mean is basically the location of the peak of the graph. So if I make the mean larger, that's going to move the normal distribution to the right. If I make the mean smaller, that's going to move it to the left. The standard deviation, on the other hand, is essentially the distance from the center of the graph to the edge. And if I make it larger, that's going to make the graph shorter and wider. If I make the standard deviation smaller, you get a more narrow, taller graph. So this is a small standard deviation, relatively speaking. Here is a larger one. So this one, the standard deviation is about 0.6. You can see here is a 1. And you can see that my dot for the standard deviation, this point is right over the 1. If I make the standard deviation 2, now this dot is right over the 2, and so on. All right, so keeping this in mind, here are three distributions, all of which are drawn on the same scale. So the first question is, which two distributions can be considered normal? All right, and if you said B, that is wrong. A and C are the ones that look more or less normal. Of those two, which one has the larger standard deviation? Well, the larger standard deviation is going to be shorter and wider. So, C. Now, because the mean and standard deviation describe a normal distribution exactly, they're called the distribution's parameters. So, you can think of parameters as the true values, whereas point estimates are the approximations. And to distinguish between these two, we have two different sets of notation. So, the mean, typically when we're talking about point estimates, we use x with a bar over it, x bar. The parameter is going to be this Greek letter mu. Kind of looks like an M, sort of a U-ish M shape, but the Greek letter mu. For standard deviation, we use the letter S. The parameter is going to be the Greek letter sigma, which is the Greek letter for S. So, if your variable x is a quantity to be measured that has a normal distribution with mean mu, standard deviation sigma, then we can write the distribution in notation as n for normal, then the mean, and then the standard deviation. And again, the mean represents the center of the graph. The standard deviation represents how wide the graph is. So for instance, here are two normal distributions. The one on the left has a mean of 0, standard deviation 1. So I go normal, mu equals 0, sigma equals 1. The other one has a mean of about 19, standard deviation 4. So n for normal, mu equals 19, sigma equals 4. All right, so if you're going to sketch some normal distributions using the shorthand notation and sketch the shape, well, suppose the mean was 10 and the standard deviation was 100. Now, I gave a link on this page for StatKey. I also have a calculator embedded in the homework. You can use that as well. So if I said the mean was 10 and standard deviation 100, I'll change the mean here to 10. 100. And you have to calculate. You can see there's a graph right there where the peak is over 10, and now the numbers are going to spread out so the standard deviation is 100. My next one was a mean of negative 100, standard deviation of positive 10. So if I change the mean to negative 100, standard deviation to positive 10, and you can see that the peak is at negative 100. And now this best represents about 3 standard deviations either way. So this has a standard deviation of 10. In the third case, mean of 100, standard deviation of negative 10. So if I change the mean at the top to 100, standard deviation to negative 10. In this case, no, nothing actually happens here. Well, technically in this case, you would have an error. Standard deviation can't be negative. But I guess with computers, you can. So for mean of 10, standard deviation of 100, that's normal in mu equals 10, standard deviation 100. And there's one graph of that. For a mean of negative 100, standard deviation 10, it's in mu equals negative 100, sigma equals 10. And there's the graph. You can see the peak negative 100. For this third one, it doesn't actually exist, despite my calculator and WAMAP. So standard deviation has to be positive.